Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we will continue with Chapter 13 on Principal Component Analysis. We just finished looking at a principal component analysis of summer and winter temperatures of selected cities around the United States, and we'll now discuss how to interpret principal components, and I'll give you one fairly straightforward strategy for doing so. I think if you're going to use principal components, that you should always try to interpret those linear combinations of principal components. And sometimes the interpretation is fairly tricky, and sometimes it's straightforward. And there's some degree of creativity involved here in making sense of what these linear combinations mean. So the coefficients in the loadings of a principal component decomposition, that's these numbers here in front of each variable, they reflect the relative contributions of features to the linear combination. And for interpretations in my class, what I encourage you to do is to look at the sign of the coefficient, whether it's positive or negative, and not really focus on the magnitude, except that maybe to consider that some magnitudes are very close to zero, so basically contribute very little, and some magnitudes are larger, either positive or negative, and that those magnitudes are contributing substantially to a component. So when you have a weighted average or a linear combination of features, say that they're with all positive or all negative loadings, let's focus sort of on all positive loadings, then that's the case. That's like our first principal component in the temperature data set. This shows how the two variables vary together. So principal component 1 describes how, as the January temperature increases, how also does the July temperature increase. So principal component 1 is a weighted average of these two variables and is how they vary together. We can also have opposite signs. Can't quite get everything on the screen at the same time. So a difference, so if z was the difference between x and y, as our second principal component is, so we have a negative January loading, and we have a positive July loading. That's the difference and represents a comparison between x and y. So consider when z equals 0, this difference. That's the case where the difference equals 0. And maybe the interesting part is where when x is greater than y, then z is positive, and when x is less than y, then z is negative. So that's showing you the area, the regions where that difference is either positive or negative. So it's representing that contrast between those two variables. In the case of principal component 2, we have a negative loading for January, a positive loading for July. And so this is showing cases where a difference between the January and July temperature. There are regions where this relationship basically equals 0. So you can imagine a January temperature that is high and a July temperature that is low, and there's a temperature there that would give principal component 2 equals 0. And so when basically that happens, when January is high and July is low, that's a value where principal component is low, principal component 2 is low, and where there's very little contrast between the two temperatures, a very steady temperature for a particular city. But where this contrast is high, say when January is very low and July is very high, then this contrast is very big. So that's a city that has a high principal component 2, which describes that we have a big difference between those two temperatures. So a lot of variability in temperature over the year. So principal component 1 basically says the degree to which these two temperatures vary together, and principal component 2 says how they contrast each other over the year. So this last paragraph is basically about how you can simplify the interpretation. When you have loadings that are close to 0, then you can sort of mentally eliminate features from a principal component to basically say that a certain variable doesn't contribute very much. Let's look at 2 examples. The first is about painted turtle shells, and the second will be about the size of sparrows, the bird. So this is a data set that we're going to look at a couple times for multivariate methods. This first example, we're going to look at female turtles, and we're going to look at the size of their shells. And these shells are going to be measured in millimeters, and we're going to capture the length of the shell from nose to tail, the width of the shell from side to side, and the height from bottom to top. So we'll read the data set in, we'll look at the structure, and we've got length, width, and height. These are integers in millimeters. Oh, yes, that's right. So that 100 millimeters is basically 10 centimeters tall, just a few inches. I'm going to plot the data in 2 ways, and we'll go back and look at the code in a moment. Here's a scatterplot matrix of the length, width, and height of the shells, and you can see very high correlations between all these measurements. Basically, as a turtle grows, the shell grows in all directions at the same time. So this is maybe not a very surprising result. All the correlations are about 0.97. And on the right-hand side is the same information but plotted in 3 dimensions. The visualization here plots these vertical lines down to the length-width axis, so you can see where the points fall on that scatter plot on the bottom. That length-width axis is effectively this axis up here. We have length on one axis and width on the horizontal. So that's where all the bottoms of the bars land, and then the vertical heights are the heights of the shells. And so it gives us this perspective of where the points are in space. Sometimes this plot can be a little hard to read because the points occlude each other, they fall on top of each other, so the relative positions in all 3 dimensions is a little bit hard. There's other ways to view this data, and I actually have this commented out here, and it would be worth me very quickly showing you how to view this type of data in 3 dimensions. So I started up RStudio. I'm going to go to the website and bring up the R code for principal components, and I'm going to look for the shells data set and run the lines that read the data set in. Excuse my previous work here. Let's start a new, I'll just paste it to the console. And so I've got the shells data now in R, and I'm going to go back to the code here, and I'm going to output this code. I'm going to remove the comments. So the RGL library is going to give us a set of functions that allows us to use the open graphics library that is a open source set of graphical tools that have been converted to be used in many different computer languages. There's a version for C and C++ and Python and R and all these other languages. And we're going to use this function called plot 3D. So I'm just going to run this here, and we'll get a graphics device that is pretty simple, but it allows you to, if you click somewhere and drag, it allows you to rotate the axes and get a sense of what those 3 dimensions are. And I think this is the right way to look at 3-dimensionally plotted data, effectively by looking at a bunch of 2-dimensional images in succession to show the relationships. And in fact, one characteristic I see as I rotate this around and find a particular orientation, you can see that there's actually a little bit of curvature in one direction. Almost like turtles grow a little bit faster in one direction, and then as they get a little bit bigger, change the direction, and they grow a little more. Now, one challenge here is that it's easy to lose track of where the axes are. So this this is the length axis that's labeled here, and right now we have 100 on the left and 160 on the right. But you can actually rotate this around enough so that here's length now down here, and 100 is on the right and 160 is on the left. So an increase is going from the right to the left. So you have to be careful when you're finding orientations that you're looking at. Here's looking right down the barrel of the data. And you can still see that curvature a little bit. Anyway, play with this if you like. It's too easy to sort of get captivated by moving all those points around. So go back here. All right, how do we produce those plots? The first is just using GG pairs. We're pretty familiar with that. And the second, we're using a library called Scatterplot 3D. And there's a function called Scatterplot 3D. Within that same library, you assign the X, Y, and Z variables. And the rest is I'm just putting in the title. The type H, the H draws these lines to the horizontal XY plane. So the H gives us those vertical bars for perspective. It can be actually really disorienting if you have just the points in space, because you don't have them anchored with respect to one of the axes. And then finally, color blue point character 19. 19 is the number that indicates filled circles. I forget what the default is. They're probably black and probably black small dots or something. So I've customized it a little bit. Let's do our principal component analysis. Now right away, by looking at this plot, you can imagine what the first principal component is pretty easily. It's the one that goes right down the axis of all these points. And then there's going to be 2 other small principal components that are orthogonal to that main diagonal component. So we'll soon find out what those other dimensions are. Here's my principal component analysis. Now recall, length, width, and height are all on the same scale of millimeters. So whether we do this on the covariance matrix or the correlation matrix, it's likely not going to matter very much. Here is, in the summary of the principal components, the summary of the standard deviations. So we've got standard deviation of 25 along that long axis of the data, and then along the 2 shorter axes perpendicular to that long axis, we have very little variability. When we look at the proportion of variance explained by that first component, 98.6%. And then we only have about 0.1% in the second component and about 0.4% in the third component. And here, finally, is a useful example for the cumulative proportion. Here's the 98% as the first component. The second cumulative proportion here is the sum of components 1 and 2. So when we add these 2 numbers together, we get 99.6 almost, the proportion of the variance explained by the first 2 components. And when you add finally all 3 components together, then you get a cumulative proportion of 1. The loadings, this is what we're going to interpret. The first component, we have length, width, and height are all positive numbers. That shows how the shell all grows together. And the relative magnitudes here are interpretable in this case. It basically here at the size or the length of the shell forward to back grows at about twice the speed as the width, which grows a little bit faster than the height. And those are effectively the relative sizes of the turtle shell. Some people describe this first component as being the mean, and it represents that in some cases. So these are the relative scales of the average turtle shell, effectively, as it grows. Component 2 has a positive length but negative width and height. And then component 3 has negative length and width but positive height. And we'll interpret those in just a minute. In fact, right now. Here I've written them out as equations. So principal component 1 is just a weighted average. I've already sort of discussed the interpretation of that. And if I page up again for a moment, this explains almost all the variability of the data. It may not be interesting to look at the residual 1.4% of the variability in this data set. So these two components may be of very little interest at all. If we were to remove these, we capture almost all the variance, and we've reduced our problem from 3 dimensions down to 1. That's a huge simplification. And then we could do all of our analysis using just this one principal component. So we could do one sample t-tests, for example. So let's think about, let's interpret these other principal components even though they're not that interesting, but just as a practice. Principal component 2 is the difference or contrast between the length and the relative height and width combined. So what shape does that describe? So think of the length of the turtle shell from front to back. And then we have basically the girth, the width and the height, sort of how big the turtle is around sort of if you were to take an axial slice of the turtle across its body, that's the comparison, that's the addition of width and height. So this basically says how not really skinny the turtle is, but sort of how long it is relative to its girth. In this case, we have a negative value for the length here, so that as principal component 2 increases, the length would decrease and the width and the height increases. So that basically, for large values of principal component 2, we're talking about turtles that are really around and not that long. And going in the other way, if principal component 2 was going negative, then we would have long lengths but really short heights and widths. So we're talking about sort of long and skinny turtles. So that's that dimension The third dimension is, the last dimension is always what's left over. But let's give a interpretation of this anyway. Here we have a negative sign for both length and width versus the height of the turtle. So if we look down at the turtle from the top, the length and the width is, if you look at the shell from the top, almost imagine it like a coin on the ground. These first two values represent sort of how round that turtle is relative to its height. So let's see, a positive principal component 3, as you increase it, we're getting higher, but smaller in terms of its length and width. So that's a turtle that's really tall, almost like a soda can, tall but not that long or wide. Whereas if principal component 3 decreases, then we're going to show an increase in the length and width, but a decrease in the height. So that's a turtle that's getting flat to the ground, like a coin. So those are the directions in principal component 3. My hope for you is whenever you calculate these components is to be able to have that sort of interpretation for each one. And as you see, it takes some visualization, mental visualization. This is hard to describe in words over a recording like this. If I had some chalk, I could draw some pictures of what extremes of these principal components could look like. But I'm hoping you're able to follow along with these visualizations or my descriptions. I'll just tell you right now that the PCA on the shells basically gives you the same results. So I'll allow you to look through this. We actually get very similar. We get similar components. The last component is a little bit different. Actually, it looks like these two components switch, component 2 and 3, in terms of their importance. However, their amount of variability explained is roughly the same, both about 0.1. So still we're getting about 98% of the variability for the first component, and then almost nothing for the others. All right. I'm going to skip this section for now and come back to it in the next video, and instead look at the second larger example, the sparrows data set. So there was a severe storm in 1898, and lots of sparrows were taken to the biological laboratory at the University of Rhode Island. So the storm was really violent, and they basically went out and collected a bunch of dead birds. And for each of those birds, they measured, for a sample of the 49 females in the sample, several measurements. So here's an image of a skeleton of a bird, and these are the measurements that were taken. The total length, which is basically if you stretch a bird out from the tip of its beak to the tip of its tail, and probably in terms here the skeleton. So if I can get it out of there, the tip of the pubis, I think, or maybe the pygostyle. I don't know exactly where they take that measurement from. The alar extent. Okay, so we have total length from nose to rear. We have the alar extent. The alar is the distance from wingtip to wingtip. So it's basically a measure of how wide the bird is when its wings are straight out to the side. Then we have 3 other measurements that are subsets of the first 2. We have the beak head length, so that's a component or a proportion of the total length. We have the humerus length, which is the length of this large bone in the wing. That's a proportion of the alar extent. And then we have a length of the keel of the sternum. So the keel here is like the chest bone, and that's a proportion of the total length. So the total length variable, the head beak length, and the total length of the keel all represent length of the bird from nose to tail, and then the alar extent and the humerus length are describing the length of the wings. So I'll read the status in, we'll do principal components, and we'll take a look at the loadings, and we'll interpret those variables. Let's start with just a plot of the data. We'll zoom out a bit so we can see all the variables together. Okay, that's tiny, but I'll zoom in a moment. We've got the total length, alar, beakhead, humerus, and keel. That's the same order that they were described before. And one major feature you see in all this is that positive correlation among all the variables. Just that birds basically have a particular shape, and as they grow, they keep that shape. And so that's this general positive relationship. Small birds look like big birds, just different sizes. The alternating variables, so total, beak head, and keel, so the first, third, and fifth variables all relate to the length variables, and then the second and the fourth relate to the wingspan. So not much to see here except that all the correlations are above 0.5 and almost as large as 0.8 for some of them. So we'll start with principal components. We'll toss in all of our variables and start off by looking at a summary. And my eye often first goes to the row for cumulative proportion. One comment here, principal component 5 wrapped onto the next line. So the first component gives us 86% of the variability. The second component gives us 97.5% of the variability. So we're already almost at 100% after only 2 components. The third one gets us up to 99, and we're talking trivial amounts on the last 2 components. The proportion for each component, 86 and then 11, and then it drops down to 1. So it seems to me on first inspection that maybe 2 components is as many as we really care about. It captures almost all the variability, and the last 3 components each contain less than 2% each. If we look at the loadings, and this is sort of an interesting thing. I want to show you this really quickly. If we go to the Sparrow data set, read that in, do the principal components and the loadings. I'll show you in R what the default is. It's going to take a second and produce a plot we don't care about. And let me resize my window. It's falling off the bottom of the screen. And it still is for some reason. Okay. Okay, give me 1 second to clean things up, then I'll describe what's happening. All right, so if you ask for the loadings of the PCA and press enter, the loadings here, you can see there's a bunch of missing spots. And that's because if we look at the help for loadings, the help will describe that there's a cutoff in printing the loadings of 0.1, meaning that any loading that has a coefficient of 0.1 or lower in magnitude, so from negative 0.1 to positive 0.1, any of those values are going to just be removed and from your view, so that visually you're going to treat those as 0. So when I look at all these loadings, the first component basically includes the total, the alar, and the keel. And the beak and the head values are less than 0.1, so I'm not even going to display them. So what I've done to actually show all the values is I'm going to use the print statement around loadings and specify a cutoff of 0, meaning that I'm going to show all the values, unless actually the value is 0 exactly, but that will never happen. So if we go back to the lecture notes, that's what I've wrapped the loadings function in the print and cut off 0. That way I get all the values. And you can see these 2 numbers right here are both less than 0.1. That's why they weren't displayed in the default printing of the loadings. That's sort of a general comment to add here, is that when you see something unusual, just look at the help and you'll often see the reason for that if you can read the options for the functions. All right. One major comment here is that actually the first component has all the same sign. So that's just how all the variables relate together. That's generally just the size of the bird. All right, let's look at a couple. I think I've got a plot. Oh, I see. So the first principal component is on the covariance matrix because that's the default. The second one is on the correlation matrix. This is, again, a third example where all of the variables are measured on the same scale. And so we're unlikely to really have very different relationships, whether we're on the covariance matrix or the correlation matrix for the principal component scale of the analysis. Here we do see some differences in terms of the cumulative proportion. The first component now is only worth 72%, then 82% the first two, the third gets us up to 90%, and so on. So these lower components, or rather these higher components, component 3 and 4, are worth a little more value. They're worth a little more than half a percentage of variance each, whereas before they were much lower. But I think many of the same relationships are going to hold. Let's plot this data using the same plots we had in the temperature example. The biplot shows us the first two components, component 1 and component 2, and shows us the original directions of the components or of the variables. I find these plots to be fairly confusing. Component 1, maybe one way to interpret this, component 1, you can see all these variables are in the point to the right, and their magnitude going to the right are their coefficients. So they're all positive, and they all have roughly the same coefficients. Component 2 has Kiel and total as positive, and the other 3 is negative. So let's go up and see that relationship. Total and Kiel are positive, and total is almost 0, and then the rest of them are negative. That is the relationship that we see for component 2. There's 0 at the origin, and both of these arrows point up a bit, and then these other 3 arrows point down. That, I think, for some of us may not be a very useful way to see the data. Here's the scree plot for the PCA on the correlation scale. We can see principal component 1 is a huge proportion of the variance, and then it sort of falls off. So the question here is, how many components should we keep? Should we compute just this one? Should we include components 1, 2, and 3, and then drop 4 and 5? It's hard to say. There's some general sort of rule of thumb ideas for how many components to keep if your goal is to do dimension reduction. One is the elbow criteria. So you can imagine if this represented an arm, sort of the upper arm and then the forearm, you can see sort of how it bends. And so this bend going down and then across, that bend suggests where you should cut off. So by that criterion, we would keep only the first component. Other ideas are about what proportion of the variance do you actually want to keep. And so in that case, you would look along the cumulative proportion and say I want to compete at least I want to keep at least 90% of the variance, then I would keep the first 3 components, because that gets us up to 90%. Let me scroll up to the first analysis on the covariance matrix, and let's interpret these loadings. And we'll just look at the first 2. The first one has all the same sign; they're all negative. That describes that's the relationship of how all these vary together. So that's generally just the size of the bird. In this case, when component 1 decreases, that makes birds larger, and as it increases, it makes birds smaller. And it's that opposite direction because of the negative sign. Let's look at component 2. For component 2, we have the total, beak to head, and the keel are all the same size or sign. They're all positive. So all 3 measurements indicate the length of the bird from head to tail. And then the alar and the humerus, those both represent the wingspan. So component 2 is about the shape of the bird in terms of, is it long with short wings, or is its body short and it has long wings? So it's that comparison. And you can interpret these other components in a similar way, though because the proportion of variance, in my point of view, we get 97.5% of the variance after component 2. So I'm not that interested in components 3, 4, and 5. They might largely represent just noise or sampling variability. When I come back in the next video, we'll review the section that I jumped over, which is why is PCA a sensible variable reduction technique, and then to show how you can separate variables by different components. And then I've got this last example about how to use PCA as a variable reduction technique in regression. So some important ideas coming up.